Okay. All right. Those of you who just sat from my ever class, hopefully you'll find this less painful, or if nothing else, it'll be shorter, or it should be anyway. Now, let's see. Continuing with the wave equation and D'Alembert solution. Okay. All right, and also some boundary conditions that are often used with a wave equation. Okay. So a quick recap. For this wave equation, here we have a Cauchy problem wave equation. So no boundary conditions. We're on a whole real number line with our two initial conditions. That this is a solution formula that was arrived at last time. So now we want to try to interpret how the solution behaves based on the initial data F and G. Okay. So I'm going to break this down into cases. So because so du dt is velocity of a vibrating string. So we assume that there is no velocity at time 0. So we only have an initial displacement of a vibrating string. So in this case, the solution just reduces to this. So what that means is, if you want the solution at any particular x and t, then what you're doing is you're taking that solution as the average of values of the initial data at two select points. That if you were to draw plot the point xt, like you're looking at the xt plane, so then you're drawing lines from that point xt back to the x-axis to locate the points x minus ct and x plus ct. And I don't have a diagram handy here, but I think I have one. Yes, I do. Okay, I'll put this up in just a moment. So more specifically, if you want the solution at a certain point, which I'll call x naught t naught, then all right. So really, what you're doing is you're backtracking along these lines where x minus ct is equal to x naught minus ct naught for a particular point x naught t naught that you have. So these two equations define equations of lines that pass through the point x naught t naught, and you're trying to backtrack along those lines to the x-axis. So to show you what those lines look like, okay, so what I need to do is I need to share my whole desktop. Okay, here we are. So here's a point x naught t naught at which you want to know the solution. So here we have the line that has this equation, x minus ct is equal to x naught minus ct naught, and here x plus ct is equal to x naught plus ct naught. So then you backtrack along these lines that satisfy these equations to the x-axis, and you look at what is the initial data at these 2 points along the x-axis. What is f of x equal to at these points? The average of those values will give a solution at this point. So this could lead to some interesting behavior, especially in cases where the initial data is 0, except at certain points. All right, and so that's what I'm going to look at right now as an example. So let's suppose this is our initial data. It's equal to 1 when x is between -1 and 1, and 0 otherwise. Then the way the solution behaves, and I'll summarize it right here, but I'll also show you. So what happens is, between these lines, x plus ct is equal to plus or minus 1. So the endpoints of this interval, or x minus ct, is equal to the endpoints of this interval where the initial data is non-zero. If x and t falls within those regions, then the solution will be equal to 1/2, because what will happen is one of these terms will be getting a value of f at a point, x minus ct or x plus ct, where the initial data is equal to 1, because x minus ct or x plus ct will fall within this interval. Now, where these two regions overlap, then both x minus ct and x plus ct fall within the range -1 to 1. So then you would get a value of 1, because you get 1 from here, 1 from here, you average them, and you get 1. On the other hand, if x minus ct and x plus ct are both outside of this range, then so this would apply, and your solution will be 0. So to show you what that looks like, basically a diagram of how the solution behaves in different regions of the xt plane. Oh, not this one. Yeah, this is the one I want. Okay, so here we have a region between the lines x plus ct is -1, x plus ct is equal to 1. And then similar over here for x minus ct between -1 and 1. So each of the regions where it's shaded, that's where the solution is equal to 1/2. So because basically what's happening in the solution formula, here we have the graph of f of x shifting to the right. Here we have a graph of f of x being shifted to the left. So what we have here is the solution is a combination of a wave traveling to the right and a wave traveling to the left. So that's what we have in this case. So here we have f of x being shifted to the left, going this way, and this way. So it's like half of it's going to the left, half of it's going to the right. In this triangle down here is where you get contributions from both the left and right traveling waves. So those contributions are added. So the 1/2 from here and the 1/2 from here add together to give you 1. Anywhere else, so out here, in between here, out here, you get 0. Because, like, for example, if I pick a point, say, right around here, then I'm going to follow these same lines parallel to these down to the x-axis. I go this direction, I land out here. In this direction, I land out here. Both places where I landed are outside the interval -1 to 1. So I get nothing. Whereas if I'm over here, you see where my arrow is, and I follow those same lines, x minus ct going this way, lands me outside, whereas I follow that line down to here, I land at a point that's inside the interval -1 to 1, so I get a contribution from to this wave. So the solution's equal to 1/2 here. Same thing if I pick a point over here. But if I pick a point outside of these shaded regions or outside of this triangle, then my solution will be 0. So any questions about how the solution behaves in this case? All right. So this sort of thing happens when you have a initial displacement being 0, except in some subinterval, that your solution is actually going to be 0 in most of the xt plane, except where you have that interval where it's non-zero basically being shifted to the left and to the right. Now let's do the opposite case. Something's wrong here. Dang it. Sorry, this thing is not cooperating. Okay. So I need to try to make this bigger so I can actually see what I'm doing. Usually I'm able to do that by zooming in, and it's not cooperating. All right. I'll just have to make do. So now we're going to have a case where the initial displacement, f of x, is 0. And we have some function g of x for the initial velocity. So then from the solution formula, this is what we have. We just have this integral of g from x minus ct to x plus ct. Okay. All right. So now what's happening is the solution at a certain point comes from evaluating this integral. So what if the initial velocity g is 0, except for some small portion of the real line? So we'll have the same function for g instead of f. Okay, so it's equal to 1 from -1 to 1, 0 otherwise. Then we're going to get some very different behavior because of initial velocity instead of initial displacement. So what ends up happening, here the solution formulas between these lines, like a shaded regions from the last example, and I'll show you this in a moment. When those two regions overlap, the solution is equal to t, and then in between the two regions where the solution was 0 before, it's now equal to 1 over c for whatever c is. Outside of all this, it's equal to 0, just like in a previous example. So I'm going to show you a similar diagram to explain where these different solution formulas come from. All right. So what happens in I'll just go for these different regions and explain each one. Now, I'll focus on the regions where it's non-zero first. So let's consider region 2, this band right here. So what's happening in this case, your solution is an integral of g from x minus ct to x plus ct. But the thing is, you're integrating g, and g is only non-zero from -1 to 1. So really what you're doing is you have to compare the interval x minus ct to x plus ct to the interval -1 to 1. And you have to find out where those intervals overlap. Now, if those intervals do not overlap at all, that's when you're way out here, region 1, region 5. So in that case, you're integrating g over a region where it's entirely 0. So that's why you get 0 in these cases. In regions 2, 3, 4, and 6, there's at least some overlap. All right, so back to region 2. So in this case, x plus ct is somewhere between -1 and 1. Whereas x minus ct, since we're not in this band, like we're over here, x minus ct is less than -1, because here's where it's equal to 1, here's where it's equal to -1, but we're over here. So x minus ct is less than -1. So then for the solution formula that we use here, we do not start integrating with x minus ct as a lower limit. We use -1 as the lower limit. Now, wherever g is non-zero, it's equal to 1. So when you compute the integral, all it is it's the difference of the limits, and then you divide by 2c. So that's what happens over here. I'm taking, let me make this a little bigger so you can read the text. Here I have x plus ct is the upper limit, minus -1 as the lower limit. So I get 1 plus x plus ct, and then I divide by 2c, and that's my value of u whenever I'm in region 2. Region 4 is similar. X minus ct is between -1 and 1. So whatever x minus ct is, that's my lower limit of my integral. X plus ct is equal to -1 here, +1 here. Over here in region 4, x plus ct is greater than 1. So my upper limit of my integral will be 1. So then my result is 1 minus the quantity x minus ct, and then I divide by 2c. So I'm going to fill in here for these regions. The interval you're actually integrating over. So in this case, region 2, it turned out to be the interval from -1 to x plus ct. That text is a little big. I don't know if I can make it smaller. Oh, I can, okay. All right, whereas over here, the interval of integration is x minus ct up to 1. Okay. All right, and that leads to these expressions that we see here for u. Now, what about here where they overlap? So in this case, x minus ct is between -1 and 1, and x plus ct is also between -1 and 1. Okay, they haven't given me enough room here. So what I would end up doing is, okay, I'll just put it over here. Region 6. The interval of integration is just going to be x minus ct to x plus ct, since they both fall within -1 and 1. So I'm going to subtract these two. The x's will cancel. Now I'll get 2ct divided by 2c, and I get t for my solution in region 6. By contrast, in region 3, x minus ct is less than -1. X plus ct is greater than 1. So both my limits of integration, x minus ct, x plus ct, are outside the interval -1 to 1. But all that means is I'll just integrate from -1 to 1. So I take the difference of the limits, which is 2, and then divide by 2c. So my u value is 1 over c. So that covers all the regions. Remember, for regions 1 and region 5, you're integrating on some interval x minus ct to x plus ct that's outside, that has no overlap minus 1 to 1. And that's why the solution is 0 in those two cases. Now, in this case, we have very simple initial velocity that's equal to 0 everywhere, except in some subinterval, it's equal to 1. Now, if it was equal to some other function on a subinterval instead of 1, we still would have a solution equal to 0 out here, 0 out here. You just have to actually like evaluate that integral on these same intervals to figure out what the solution would be. All right, so okay, so some questions about this case. One thing I want to point out is, since we have these piecewise definitions for the different regions, what happens when you cross a boundary, like say from region 2 into region 6? So we have this line segment right here that's the boundary between them. Well, on this line, x minus ct is equal to minus 1. So, okay, so I'll note this over here. So, boundary between regions 2 and 6. So we have x minus ct is equal to minus 1. So now if you look at the solution formula over here, 1 plus x plus ct over 2c. If I figure out what that is, in this case, x minus ct is equal to minus 1. I can use this to solve for x. So x is equal to minus 1 plus ct. So now I have this. So minus 1 plus ct is equal to x. Well, the 1 and minus 1 cancel, and then the ct's add together, so I get 2ct over 2c. Well, all that simplifies to t. So it turns out that these solution formulas, 1 plus x plus ct over 2c and then t, are compatible on this boundary. In other words, we find that the solution is at least still continuous in spite of this piecewise definition. Or at least it's continuous at this boundary. But the initial data is discontinuous because it's equal to 0 everywhere, except it jumps up to 1 here and here. So although it's continuous at this boundary, and we would find the same at this boundary, but does not necessarily mean it's continuous everywhere. Let's see. X plus ct is equal to minus 1. Now, let's see. Over here, where x plus ct is equal to minus 1. Okay, yeah, here the solution is going to 0. Okay. All I'm saying is, in general, discontinuities in the initial data are not necessarily smoothed out. With a heat equation, the heat equation has a very smoothing effect. If your initial temperature profile is as a jump discontinuity, you would find that the solution of a heat equation is still going to be smooth. That whatever jump you have gets smoothed out immediately. It's not necessarily the case for the heat equation. But what happens here is, actually, I believe in this case, you're going to have a continuous solution because G is G is piecewise constant, but it gets integrated. So when you have a function that is piecewise constant and then or piecewise continuous, and then you integrate it, the result that you get would still be continuous. So that's why the solution will be continuous in this case. However, if we go back to the previous case where we had zero velocity but a non-zero displacement for initial conditions, here we have a solution that is 1/2, and then 0 or 1. So here we have discontinuities across these boundaries. So whether you have that or not, it's going to depend on the nature of your initial data. So if your initial displacement has discontinuities, those discontinuities can persist, and that's exactly what we see here. Discontinuities in your initial velocity can still lead to continuous solutions, and that's what we see here. Okay. So questions about these cases? Now, so far, we've only been looking at the Cauchy problem for a wave equation, so domain of the entire real line. But let's look at a semi-infinite string, so domain from 0 to infinity, and see how we can handle that case. So here's a wave equation, same kind of initial data on 0 to infinity. But now at x equals 0, we impose a boundary condition. We're going to assume that the solution u is 0 at the left at this one boundary. So this is a Dirichlet boundary condition. So we have a fixed displacement of 0. Now, to try to solve this, we can proceed like last time. We do the same change of variable. We get the same simplified PDE. We have the same general solution. So our solution u of xt is some function of x minus ct plus another function of x plus ct. Now, so what we could do is, and this is just repeating what I did last time. We apply the initial conditions to this, and solve a resulting system equation. So we have this for phi, and also psi. So this part is no different, but now we have a problem because we're on the domain from 0 to infinity, because x and t are assumed to both be positive. So if x and t are both positive, x plus ct is positive, so we can go ahead and use this. There's no problem here. But this could be a problem. X minus ct might be negative. So this cannot be used, and we cannot assume anything about the initial data f or g when on the negative portion of a real line. So this formula as written can only be used if x minus ct is positive. We have to figure out what we're going to do whenever x is less than ct. So for any particular t value, for x sufficiently small, this is invalid. So the way we get around this is to use a boundary condition. So if I plug in x equals 0 into my form of a solution, so I plug in x equals 0 here. then here's what I get. 5 minus CT plus 5 CT. And that has to be 0 because that's the boundary condition. So now I have this relationship between phi and psi. And keep in mind, from what I have up here, psi is okay. I can go ahead and use this. So this gives me a way of defining psi. This gives me a way of defining phi for negative arguments. All I have to do is use psi with a positive argument and then negate it. So now, let's suppose that x minus ct is negative. So then 5x minus ct will be minus phi of its negation. If x minus ct is negative, ct minus x is positive. So now I can just go ahead and use my formula for psi. I just have to negate it. So now I have a formula for u of xt in the case where x and t are both positive, but x happens to be less than ct, therefore making this negative, therefore making this positive. So here's my solution formula in this case. So notice it bears a very close resemblance to the elaborate solution. It's just that, first of all, this limit was x minus ct, but now it's ct minus x. Same change over here. And then this was a plus, but now it's a minus. Meanwhile, if x is greater than or equal to ct, I can just use the same old formula. So the way this solution behaves, because of this boundary condition at x equals 0, we end up seeing a reflection of waves at the boundary. And I want to see if I can check and see if the book has a picture of this. Yes, we do. So what ends up happening is, okay, this is particular initial data. Okay. All right. So let's suppose we want a solution at this point, x naught, t naught. Now, the way this normally works in a wave equation, a Cauchy problem, you draw this line according to this equation down to the x-axis, and you see what f of x is here. And then you also draw this line down to the x-axis and see what f of x is over here, when the domain is a whole real number line. But because it's not now, because we have this boundary at x equals 0, you start to follow this line, and then it bounces off the boundary and goes here. So this is the initial data that's referenced. So that gives you an idea of how the solution is going to behave because of its boundary. And so the kind of propagation that we see, like if you were to solve this equation with initial data like in previous examples, like initial displacement that's 0 except for a certain interval, that we end up seeing propagation to the left and right like before, but that wave ends up, like suppose you have a wave that's propagating starting from here, going to the left. It hits the boundary and reflects back. So that's the effect of this boundary condition. Okay. So questions about how this formula was obtained. There's one thing I want to check about the homework for these lessons. Okay. So for this lesson, I'd assigned problems 1 and 3, and I want to take a look at those real quick. Okay. Oh, those are no center problems. Okay, this is what I want here. Okay. Oh, yeah. First problem is solving that for a specific example. And then problem 3. Okay. Problem 3 is very similar to the example that I just worked out, except first there's a simplification that there's no initial velocity. So g is 0, so you can ignore the integral part. But look at the boundary condition. Is du dx at x equals 0 is 0. So what that means is when you find yourself in the same situation where you have this solution formula that you like to use, and you have the same dilemma as before, that this cannot be used if x minus ct is negative, then you're going to go back to here and take the derivative of this whole equation, both sides, with respect to x, and then substitute x equals 0. And that will give you a condition similar, not the same, similar to this one, to figure out what your solution formula is going to be, something along these lines, where there's some change to D'Alembert's solution for that kind of boundary condition. So you're following this kind of derivation, you're just changing this one step because of the different boundary condition. But you do that by applying a boundary condition here. So differentiate this with respect to x, then plug in x equals 0. Okay. Now, the last thing we'll talk about is boundary conditions that we might have for a wave equation. Okay, so now we're on a bounded intervals. So x is going from 0 to L. We have the same kind of initial data. So what kind of boundary conditions might accompany the wave equation, and what would they mean? Okay, so first, suppose we have the displacement fixed at the endpoints. So that's like with a heat equation, Dirichlet boundary conditions. So U is set equal to something at the two boundary points that may or may not be a function of T. Next boundary condition. It's where a force is specified on the boundary. So vertical forces at the endpoints are given by the tension times plus or minus the first derivative with respect to x. So here we have du dx at x equals 0. At the right endpoint, x equals L, it's minus du dx. In other words, we have the inward normal derivative. So if we set these equal to something, we get what's called a Neumann boundary condition. So Dirichlet boundary conditions are where U is equal to something. Neumann boundary conditions is where du dx, or for higher dimensional problems, the normal derivative is set equal to something. So here, if the ends of a string are allowed to slide vertically, then so basically we're free to move instead of being fixed like they are here. Then the du dx is equal to 0 at both endpoints. All right, next. All right, if the ends of a string are attached to springs, then we have what are called mixed or Robin boundary conditions that involve both du dx and U. You remember seeing these kind of boundary conditions for the heat equation. In that case, that applied to like one end of a rod being placed in a medium, and the boundary condition depends on the temperature of a surrounding medium. So boundary condition would have that same form, but here's what it means in this case, where we have we're accounting for the force due to the springs. So theta 1, theta 2 are the displacement of the attachments that are the springs that are attached to the vibrating string. Because then I try to visualize these things, like what strange situations I'm describing here, but okay. Now, you do not have to have the same kind of boundary condition at both ends, which we saw with the heat equation. So, for example, you could have one end of a string fixed, and then the other end is free to move. So then we have a Dirichlet boundary condition at x equals 0, a Neumann boundary condition at x equals L. So all these different possibilities affect what kind of eigenvalues and eigenfunctions you might have, just for the same as for the heat equation. So this kind of problem on a bounded interval, x going from 0 to L, you can solve that using separation of variables. And your ODE for x, so xn of x, is exactly the same. It's just that your time-dependent equation is different, but that's still going to have the same kind of, general solution where you have a combination of a sine and cosine. So you have that for both your x and your t ODEs. All right, so these are the kind of boundary conditions that we can expect to see for wave equation problems, which are actually the same as for heat equation, just with appropriate physical interpretation. All right. Now, actually, I want to check on the site. Okay, so we actually do not have anything going on for a while. So I want to remind you, and I those of you who are in my other class, I should have brought it up there too. Next week is our so week of March 8th is our informal spring break. So during that week in both classes, I am not covering anything new. I do not have any assignments due. So it's a chance for you to catch up on things, and some people in this class or the other class need to. I will be present in Teams at the same time, so anyone can come by and ask questions. Just because I really should not simply cancel class altogether, otherwise I certainly would. And if no one shows up, then so be it. If certainly anyone has any questions at this time, feel free to ask, or you can hold them for next week. But yeah, we don't have anything due, or should I say, due until that's right, Taylor, until March 15th. All right. So, but just in case, does anyone have any questions at this time? Everybody's like, partial spring break, woohoo! Okay. All right, then I guess we're done.
I do have a question about the summer and next fall courses, but I don't know if you want to stick around for a couple of minutes.
Oh, yeah, actually, well, and I'll just put this out there for everyone real quick. Yeah, because apparently the fall schedule. Am I still recording? Oh, yeah, that's fine. Yeah, fall schedule apparently not been posted in Thor, although it is in Thor. Like, for instance, faculty are able to see their own classes. if anyone has a question about whether or something's gonna be offered or what's gonna be offered, that is something I can look up. The classes I will be teaching in the fall will be Math 721, if it's for graduate students. That's numerical methods for PDE. So basically combines this semester's classes. And the other is Math 460, 560. So that's a mixed undergrad graduate class. That's the standard numerical analysis sequence. So 460, 560 in the fall, and then 461, 561 in the spring. So does anyone have questions about fall classes?
When is this seminar offered?
Are you talking about the COS 740?
I think that's the one.
Yeah, that's the seminar that is required for PhD students, and apparently we're not going to offer it in the fall. We've been offering it every fall and spring, and I think we're switching it to just for spring.
Okay.
Yeah. And they've been requiring it twice. I feel like we should change that now. Because it used to be it's just the seminar class. Like we have outside speakers and students just show up and that's their 740 grade. But now it's a class where students give some sort of presentation. Like for instance, if they're into their research, they give it on that. And then they can critique each other and so forth. Like it's practice for eventual defense. So I feel like we should only make students take that class once instead of twice, but I've not yet been heard on that matter. And then, for PhD students, COS 703 should be offered also. And there's also Math 771. So those are required classes for Math PhD students.
The 721, how important is it? I couldn't even find MAT 720. In the catalog.
Yeah, I wonder if I got removed. I basically dusted off an old 721 that's been on the books for years and repurposed it. But anyways, but someone who is really this class prepares you quite well for it. Now, I mean, we get to the numerical methods, but I don't really assume foreknowledge of those because I mean I assume that it's generally safe to assume that students just if they did take it in every class that they've already forgotten it. So
if I didn't take 610 this semester, it's not going to kill me to take 721.
No, definitely will not. Yeah.
Okay.
Yeah, I try to make these things self-contained.
Thank you.
Yeah. Okay. I see a few people have left already, but that's perfectly fine because we're just talking about classes. But anyone else have any questions about what's coming down the pike or what's offered? And certainly I can answer that. Or anyone who doesn't care about that is free to scram.
Is there anything offered this summer?
I believe Dr. Ding is offering something. It would be under Math 684 would be the number.
Okay.
And he's done lately chaos theory. I know it's something different this time because some of you all have already had that. I think it might have been like on projective geometry or something like that. So if you're interested, I can find out.
Okay, thanks.
Mm-hmm.
It is something to do with fractals and repeating triangles and polygons.
Yeah. There you go.
Thank you. Have a good week.
All right, you do. All right.